In this problem, we are answering practice problem number 2 from the review questions in class today. Dizzy is speeding along at 22.8 meters per second as she approaches the level section of track near the loading dock of the Whistler roller coaster ride. A braking system abruptly brings the 328 kilogram car to a speed of 2.9 meters per second over a distance of 5.55 meters. Determine the braking force applied to Dizzy's car. In this question, we have a kind of a roller coaster. I'm going to draw a picture first. It starts at a velocity of 22.8 meters per second, and then it brakes in a distance of 5.55 meters to a velocity much slower of 2.9 meters per second. So the question asks, what is the force that it takes to make this roller coaster brake from 22.8 meters per second to 2.9 meters per second? What you need to know is to use the work energy theorem. The work energy theorem is just a way to equate work with a change in energy. One good way I like to describe that is work is this idea or this value of a force over a certain distance, but it's also anytime the kinetic energy changes anytime the potential energy changes, they're all equal to each other. So you have to take the givens and see which two or more values equal each other. In this case, you'll see that we'll need kinetic energy to equal force over a certain distance. And that all comes from our givens. And to write down our givens, we have a velocity here, and it's going to be an initial velocity, a velocity final here, and we have a distance. Since if we look at this situation, none of this is in terms of velocity, it's in kinetic energy. We'll probably have to use the equation kinetic energy is equal to 1/2 mass times velocity squared. And since we have a distance and we're looking for force, we'll definitely need to use force times distance. So if I'm looking at this, I actually have an initial kinetic energy with the initial velocities, which I'll go ahead and plug in and solve for. Kinetic energy initial is equal to 1/2 the mass. And the mass is, I believe, 328 kilograms. 1/2 328 times velocity initial, which is 22.8, and you square the 22.8. Don't forget to square the 22.8. If you plug that into your equation, you should get 852,000 or 85,253.76 joules. We can also go ahead and solve for the kinetic energy after, or when it breaks, and that's using the same equation just with the final velocity squared. So 1/2 times 328 times 2.9 squared, and you'll get a much smaller number of 1,379.24 joules. So if you take a look at this work energy theorem, which from our givens we decided that this would be a good idea to look at, you see that change in kinetic energy is actually equal to the final kinetic energy minus the initial kinetic energy. This triangle means change, and change is always final minus initial. So we'll just subtract 85,253.76, which comes from the initial kinetic energy. and we'll subtract it. Oh, I'll just switch it around here. We'll subtract that here with 1,379.24. And you'll get an answer of negative 83,874.52. From there, you know that the change in kinetic energy, since they're all related, is equal to force times distance, which is just another equation for work. You have a force, which is what you're looking for, and a distance of 5.55. To get force, you just divide both sides by 5.55, divide both sides by 5.55. You get a final force, or the braking force, equal to 15,112.53 newtons. If you want to round to significant figures, you would round to two significant figures, which would be either 15,000 newtons or 1.5 times 10 to the 4th newtons.